In this video, I'm going to explain the types of contour toolpaths. Contour toolpaths remove material along a path defined by a chain of curves. Contour toolpaths only follow a chain, they do not clean out an enclosed area. You can select an unlimited number of chains for each toolpath. You can create either 2D or 3D contour toolpaths. You can also create 2D chamfers to bevel the edges of a 2D contour. Contour ramp can be created for smooth transition between depth cuts. Remachine contours are also allowed to remove areas where a roughing tool could not machine the stock. When creating a 2D contour toolpath, you can add an oscillation strategy by selecting Oscillate. Adding oscillation in the Z-axis along your contour toolpaths uses more of the cutting length of the tool and can reduce the tool wear in that axis. 2D contours are used to rough and finish part walls. Multiple depth of cuts and XY passes can be applied to control stock removal and finish quality. 2D contour toolpaths typically work as follows. Tool moves above the plunge point. Tool rapids and or feeds to a specified Z depth. A lead-in move blends the cut onto the outside profile. All motion around the profile is planar. No change in Z depth occurs. A lead-out move smoothly transitions the tool off the profile. Tool retracts to save height. 3D contours are used to machine O-rings, grooves, simple ramps, and trim cuts. 3D contour toolpaths typically work as follows. Tool moves about plunge point, tool rapids and or feeds to initial Z depth. Tool moves around profile in a roller coaster fashion. XYZ motions are allowed as the tool tracks along the profile. Tool retracts to save height. When a 3D contour is selected, Mastercam automatically sets contour type to 3D and activates the maximum depth variance field. Cutter compensation for 3D contours is more complex than 2D compensation, and simply following a 3D profile with the tip of the cutter will gouge the part as shown in the figure. Accurate 3D profiling is accomplished using a surface or a solid machining toolpath. Use a chamfered contour toolpath to bevel the edges of a 2D contour. You must select a chain that represents the sharp edge of the profile. Mastercam automatically calculates the correct offset in the tool plane and depth to produce the specified 45 degrees chamfer. Chamfer toolpaths typically work as follows. Tool moves above plunge point, tool rapids and or feeds to a specified Z depth. A lead-in move blends the cut onto the outside profile. All motion around the profile is planar, no change in Z depth occurs. A lead-out move smoothly transitions the tool off the profile. Tool retracts to save height. Use ramp contour toolpaths when you want to use a continuous ramp to transition smoothly between depth cuts instead of individual plunge cuts. This technique is especially useful in high-speed machining. Contour ramping is only available for 2D contour toolpaths. You can ramp by a set angle, by a set depth, or you can plunge directly between depth cuts. Ramp contours toolpaths typically work as follows. Tool moves above plunge point, tool rapids and or feeds to initial Z depth. Tool moves around contour at first in a ramping motion to final depth. Tool continues to move around the profile to complete one full loop at the depth. Tool retracts to save height. Ramp contours are used extensively in the woodworking industry. They save stock material by doing away with planar lead-in moves, allowing parts to be spaced closer together. Remachining contours are a type of 2D contour toolpath that removes material only in areas where stock remains after a previous finish operation. Remachining contour toolpaths typically work as follows. First, finish machine the profile with a larger tool. A smaller tool is specified, and Mastercam remachining functions calculates where stock remains. The toolpath is created only in those areas. Multiple depths and XY passes can be applied to control stock removal and finish quality. Remachining can dramatically reduce part run time and tool wear, since the smaller tool, which is forced to run at lower speeds and feeds, is used only where necessary. When creating a 2D contour toolpath, you can add an oscillation strategy by selecting Oscillate. Adding oscillation in the Z-axis along your contour toolpaths uses more of the cutting length of the tool and can reduce tool wear in that axis. This is especially useful when cutting thinner materials or laminated materials such as kitchen countertops. Mastercam provides an oscillation strategy for its mill and router contour toolpaths. You can choose a linear, zigzag, or a smoother high-speed oscillation movement. You also define the maximum depth and the distance along contour for the oscillating tool movement. The top of the stock that you enter in the linking parameters page sets the maximum Z height for the oscillating contour toolpath. However, the tool will not exceed the maximum depth that you specify in the cut parameters page. The distance along contour determines how far the tool moves in X or Y before changing directions in the Z axis. If you edit the operation and modify the tool, Mastercam automatically verifies that the flute length of the tool is sufficient. A message warns you if the flute length is less than the overall oscillation distance. This concludes the video on the different types of contour toolpaths.